Structural development of skyscrapers. Abstract. This paper presents a review on the evolution of the structural system of skyscrapers from earlier to the modern and the effects of this on the society and environment. Index terms: skyscraper/tall buildings, height premium, internal, external and hybrid structural system, building loads, shear walls, lateral rigidity, lateral sway, floor vibration. Introduction. Tall buildings emerged in the late 19th century in the United States of America. They constituted a so-called American building type, meaning that most important tall buildings were built in the USA. Today, however, they are a worldwide architectural phenomenon. Many tall buildings are built worldwide, especially in Asian countries, such as China, Korea, Japan, and Malaysia. The distribution of tall buildings has changed radically, with Asia now having the largest share with 38%, and North America's at 22%, Fig. 1. This data demonstrates the rapid growth of tall building construction in Asia while North American construction has slowed. In 1857, Elisha Otis and the Otis Elevator Company began manufacturing passenger elevators. Invention of elevator allowed vertical transportation of people and goods without stair. Chicago is the birthplace of the skyscraper. The Home Insurance Building, 1885, in Chicago, 10-storied with 42-meter in height, is generally referred as the first high-rise building. Architect William Jenney. The Home Insurance Building was built followed by the Great Chicago Fire, 1871. The physical envelope of construction was traditional load-bearing system. Thick masonry external walls creates comfortable indoor thermal environment. Large window and high ceiling was provided to allow the daylight to the interiors. Maximizing the financial return over a fixed plot size, initiates the development of modern high-rise building in North America during mid-19th century. Premium for height. The primary structural skeleton of a tall building can be visualized as a vertical cantilever beam with its base fixed in the ground. The structure has to carry the vertical gravity loads and the lateral wind and earthquake loads. Gravity loads are caused by dead and live loads. Lateral loads tend to snap the building or topple it. The building must therefore have adequate shear and bending resistance and must not lose its vertical load carrying capability. Fazlur-Khan realized for the first time that as buildings became taller, there is a premium for height due to lateral loads, and the demand on the structural system dramatically increased, and as a result, the total structural material consumption increases drastically. Ali, 2001. Further to this, the columns need to be even heavier towards the base to resist lateral loads. The net result is that as the building becomes taller and the building's sway due to lateral forces becomes critical, there is a greater demand on the girders and columns that make up the rigid frame system to carry lateral forces. The concept of premium for height is illustrated in Figure 2. If we assume the same base sizes, the material quantities required for floor framing is almost the same regardless of the number of stories. The material needed for floor framing depends upon the span of the framing elements, that is, column to column distance, and not on the building height. The quantity of materials required for resisting lateral loads, on the other hand, is even more increased and would begin to exceed other structural costs if a rigid frame system is used for very tall structures. This calls for a structural system that goes well beyond the simple rigid frame concept. Based on his investigations, Khan argued that as the height increases beyond 10 stories, the lateral drift starts controlling the design, the stiffness rather than strength becomes the dominant factor, and the premium for height increases rapidly with the number of stories. Following this line of reasoning, Khan recognized that a hierarchy of structural systems could be categorized with respect to relative effectiveness in resisting lateral loads for buildings beyond the 20 to 30-story range. Khan, 1969. Classification of skyscrapers' structural systems. Internal. A system is categorized as an interior structure when the major part of the lateral load resisting system is located within the interior of the building. It includes mainly rigid frame system, vertical shear truss system, frame A shear truss system. Rigid frame system. Rigid frame or moment-resisting frame, MRF, consists of girder and column rigidly connected together in a planar grid. Such frames resist load primarily through the flexural stiffness of the members. The size of the columns is mainly controlled by the gravity loads. Progressively larger column sizes towards the base. The size of the girders is controlled by stiffness of the frame to ensure acceptable lateral sway of the building. Some of rigid frame tall buildings is A860 and 880 Lakeshore Drive Apartments, 1949, Chicago, 82 26 stories. Vertical shear truss. Vertical shear truss system, RC coupled shear wall, can effectively resist lateral forces caused by wind and earthquakes. They are treated as vertical cantilevers fixed at the base. Frame A shear truss system. Rigid frame is not efficient for buildings over 30 stories because the sway caused by the bending of columns is excessive. Vertical shear trusses alone provide resistance up to 35 stories. When vertical shear trusses are combined with rigid frame, the interactive system results in a common deflected shape of the structure. The upper part of the truss is restrained by the frame, the lower part, frame is restrained by the truss. This effect produces increased lateral rigidity of the building. Some of the frame truss buildings are the Empire State Building, 1931, New York, 381 102-storied, 311 South Wacker Drive, 1949. External, if the major part of the lateral load resisting system is located at the building perimeter, a system is categorized as an exterior structure. It is desirable to provide lateral load resisting system components as far as possible on the perimeter of tall buildings to increase their structural depth. Tubes are known as basic exterior structures. It can be defined as a three-dimensional structural system utilizing the entire building perimeter to resist lateral loads. It includes mainly frame Tuesday system, braced tube system, tube-in-tube system, bundled tube system. It has closely spaced columns and deep spandrel beams rigidly connected together throughout the exterior frames. Depending upon the structural geometry and proportions, exterior column spacing should be from 5 to 15 feet, 1.5 to 4.5 m. Practical spandrel beam depths should vary from 24 to 48 in, 600 to 1200 millimeters. Resulting structural organization: the lateral load resisted by the whole tube. Some of the frame tube buildings are Water Tower Place, 1975, Chicago, 262 m, 74 stories, Aeon. Braced tube system. It is possible to stiffen the building structure by introducing diagonal braces. Introduction of diagonals also increase the spacing of columns in frame tube. The diagonals participate in dual role action as it collect gravity loads from floors as inclined columns. Also act as a stiffener in case of lateral loads. Some of braced tube structures are John Hancock Center, 1970, Chicago, 344 m 100 stories, Ontario Center, 1986. Tube-in-tube system. The stiffness of a frame tube can be further enhanced by using a core tube to resist part of the lateral load, resulting in a tube-in-tube system. The floor diaphragm connecting the core and the outer tube transfer the lateral loads to both systems. It is also possible to introduce more than one tube inside the perimeter tube. In tall buildings with larger floor areas, simple frame tube system become very uneconomical structural solution. To overcome this, many frame tubes are symmetrically grouped together to create larger floor space. Further, these grouping of frame tubes, called bundled tubes, are actively participate to transmit the superstructure load to the ground as well as provide the lateral stability against the transverse loading. Some of the bundled tube structure are Sears Tower, 1973, Chicago, 442 m 108 stories, Burj Khalifa, 2010, Dubai, 828 m, 163 habitable floors plus 46 maintenance levels. Almost all the conventional vertical columns are eliminated. This is possible because the diagonal members in Diagrid can carry gravity loads as well as lateral forces due to their triangulated configuration in a distributive and uniform manner. Some of Diagrid buildings are Hearst Building, 2006, New York, 182M, 46 stories, Swiss Re Building, 2004, London, 181M, 41 stories. Exoskeleton. In exoskeleton structures, lateral load-resisting systems are placed outside the building lines away from their facades. The system is associated with other conventional types due to the system's compositional characteristics. It acts as a primary building identifier. Some of exoskeleton buildings are Burj Al Arab, Dubai. Superframe. A superframe is composed of megacolumns comprising braced frames of large dimensions at building corners like exoskeleton. The system is also associated with other conventional types, the megacolumns usually linked by multistory trusses at about every 15 to 20 stories. Some of superframe buildings are Park Central Tower, 1979, Caracas, Venezuela, 221m, 56 stories. Diagrid exoskeleton superframe. The frame shear truss system is further modified with introduction of outriggers band in differential vertical levels. The outriggers are generally in the form of trusses in steel structures, or walls in concrete structures. Outriggers reduce the overturning moment in the core. Outriggers can also be supported on megacolumns in the perimeter of the building, thus resisting the lateral push on the building by feet spread technique as shown in Figure 13. Conclusion. This paper has presented a general review of structural systems for tall buildings. Various structural systems within each category of the new classification have been described with emphasis on innovations. This paper demonstrates that structural systems have come a long way since the late 19th century when they were conceived as framed systems. With the development of increasingly taller buildings using lighter members, serviceability issues like lateral sway, floor vibration, and occupant comfort need to be given more attention by researchers. More research is needed for exterior structural systems which are technically more efficient.